It's good to be here. Thank you for having me here. I've corresponded with several of the CS faculty here for about 2 years now, and so it's good to finally be here in person. Who are the undergraduates in the room? Undergrads. Okay, good. You understand why I'm asking you this, right? Because there'll be questions and I'm expecting interaction, and professors, they're like reading email, but you, on the other hand, are like, write young things and chipper and all that. Okay, good. So I want to ask you all a question. So you're all, like most of you, I imagine, who are here are somehow computer science related. Yes? Oh, no, excellent, good, my people. Okay, but some of you are computer science people related, unfortunately, right? Yes, okay, good. So somebody walks into your office, they ask you a question, right? And they say, I want to teach a computer science curriculum. This is going to happen to you, right? You graduate with a degree in computer science, you're going to go out, you're going to be working in like some, high-tech office. Somebody will come and say, I want to teach a computer science course in a school. What should I teach? Okay, so what should I do? Right? What should I do? What are you going to tell them? Yell out some answers. Come on. Sorry, Matt? Huh? Who are you teaching? This is the kind of question you're going to get. Come on, I want to see if you're prepared for the question. Answers. Numbers, maths, okay, what else? Coding, good. More? Come on, good. Logic, okay. Algorithms, okay, good. You're just going down your courses one by one. Okay, come on. What else are you going to say? Coding, you're just going to say coding. They're going to say, what kind of coding? Photoshop, very good. Okay, what else? Sorry? Algebra, very good. Okay, what else? That's it? Modeling, okay. You're still naming like courses, but somebody says, okay, coding, what coding should I teach? What should I do? Economic models, okay, good. What else? Anything else? Okay, so this question came up in the Brown CS Facebook group, and you get answers like this, right? I want to teach coding to a group of 5th graders. Okay, and I took CS4 in college. I don't have much CS experience, but I'm working in a couple of elementary schools. Okay, does that change your answer? Okay, now what are you going to say? Anyone? Ideas? Undergrads? How do I get them interested in coding? Okay, that's a legitimate question, but I mean, they want answers. They don't want questions from you. Yeah, they've already asked the question. Games, game-based something. Yeah, game-based something. Solving puzzles. Okay, solving puzzles. Yeah. Sorry. Turtles, excellent. I like turtles. I mean, I like turtles as animals. I don't know about the coding part. Yeah. Anything else? Somebody said something? Huh? Scratch. Excellent. Okay, good. So, Scratch. Okay, how about that? Turtles. Okay, and then of course you always have to have the contrarians. Like, I remember wanting to learn programming, super frustrated by Logo. Obviously, you have to teach them C++, right? That's obviously the thing to teach 5th standard students. Okay, good. All right. Now, you're all, well, many of you are computer scientists. So someone walks into your office and says, I want to make software. You're the expert. What do I do? Code. But, we're getting answers in terms of concrete tools, right? Like Scratch and Logo and C++. What problem are you solving? Identify the problem. Requirements. Well, I thought you were all giving me solutions, and now you're giving me questions. Right? Because software is complicated in all sorts of ways, right? There's dependencies and fragility and complexity and all these other things, and it's completely meaningless to talk about solutions without first understanding what problem you're trying to solve. Why is education any different? There's this magical problem that computer scientists have of treating education like this thing where we come up with solutions before we ask, with one sole very strong exception, right? What is the problem we're trying to solve? Right? We start talking about solutions. So I think of education as every bit as hard as building software. Building curricula is every bit as difficult. And in fact, good engineering discipline would tell you that before you worry about solutions, you want to start by understanding what is your high-level goal, Then you want to think about what kinds of constraints do you face, and then you might think about what kinds of methods are even available, and then you might think about what the solutions are, right? And computer science has this unique problem, maybe unique, I don't know, but it's certainly very much a problem in computer science, that we start over here and sort of don't worry about the rest of the funnel that has to feed into it, okay? So what are the constraints that you face when trying to teach something in a school? Well, actually, any people in the audience, tell me, what do you think of the constraints in schools? Infrastructure, good. Can you drill that down a little bit? Lack of computer labs, good. Another answer. Interest. Okay, I mean, interest, nobody worries about interest, man. You're taking a class, you're stuck in a class. Yeah, but no, you're right. Interest is actually a problem. Good, we'll talk about that more. Other constraints, other constraints. The knowledge of the teacher. Oh, that's a very interesting one. That's a very clever observation. Other questions, yeah. Difference in skill level between the different students in the room. Okay, other constraints. See, you do know about constraints, you just didn't ask about them. Yeah, you had a hand back up there. Sorry? Peer pressure, ooh, very nice one. Okay, okay, so you're starting to see, right? What age are the students, you know, what exposure they had before. Is this a required class? In the US, you have what are called elective classes, and that makes a big difference of who's in the room. How long does it meet? If a class meets every day versus a class meets every week, what difference might it make? Why does it matter whether a class meets every day or meets every week? How much do you remember? Yeah, do you need a recap? Do you need a first 15 minutes remind them of what they learned a week ago? Or can you just assume they remember it from a day before? Ebbinghaus, learning curve, forgetting curves, right? People forget. Within a week, they forget a whole bunch of stuff that they heard a week ago. Okay? And how many students are in the classroom? Because the teacher, you have to understand what constraints are on the teacher. And is it even a class? Now, you're like, well, what do you mean? Well, in the US, at least, there are what are known as after-school activities. So after-school activities have a very different feel and structure than classes, okay? And then there's a whole bunch more things, right? Like, does the school have internet? These are your infrastructure questions, right? Does it have internet access? Do they have regular access to computers at home? Because it affects what kind of homework you're allowed to give, okay? Do they even have regular access in school? Which depends on the school and might be tied to various things, even which kind of class they're taking. Is the teacher new to programming? You were talking about the teacher skill level. Can the students type, right? People in this room, you're all very good typists, or at least like thumbists, right? But can the student even type, right? And are there students with disabilities? Do they have any like visual impairment, things like that, okay? So these are the kinds of questions you need to ask before you go in and start proposing solutions. This is the stuff that makes education every bit as complicated as building software, okay? You were all using words like requirements, right? This is the requirements engineering process for education, okay? Okay, so I want to talk about a very specific curriculum today, and I want to tie it to a national goal. It's a national goal in the US. It's also a national goal in India. In fact, it seems to be like a national goal in every single country, which is apparently we have to teach computer science to everybody. Okay? So I want to take as a starting point a very, very, very important premise here, which is just because you need to teach computer science doesn't mean that you need a course named computer science. Okay? This is a bit of a controversial position. This is actually a position that my colleague Matthias Verleisen and I staked out in 2007. Got into a lot of trouble with the computer scientists for saying this, because it's really important that you have to be a member of the union and you don't like then speak up against the union. But we believe this very profoundly, and I'm hoping in today's talk I'll give you a sense of what we mean by this. And the other thing we pointed out was, in a few years, people are going to say, everybody needs to learn data science. And like 10 more years, everybody's going to need to learn something, and we don't know what that is. How are you going to make room for all these subjects if you have to keep creating new courses, right? I mean, yes, obviously nobody needs like arts and stuff like that. You can throw that out and put in computer science. But then once you throw out everything that's been thrown out, where are you going to make room for like data science courses, right? And now, of course, everyone has to learn artificial intelligence. So we're going to throw out computer science to make room for data science and data science to make room for artificial intelligence. Like, how are we going to pull this off, right? So this is a universal problem. Okay, so here is the approach that we take. We teach computer science by integration into existing subjects that are already being taught in the school, okay? This is the key thing. We take subjects that exist And we produce a whole bunch of materials. I'm not going to go into all of this. If you're interested like education, this slide maybe doesn't make so much sense here. But we provide the spectrum of materials that's needed for teachers who are not computer science teachers or even trained in computer science to be able to teach a reasonable amount of computer science. That is our goal. Okay? And basically, our two main curricula, we have an algebra curriculum and a data science curriculum, and both of these have some commonalities. We work with middle school students and high school students. They have no prior computing experience, and in the algebra case, which is what I'm going to talk about today, we have them build a video game. In the data science context, they build reports, data-driven reports, and there's a choice question, which is going to be a central part of my talk, we'll come to later. And they do it in a module rather than taking over an entire course. So it can be integrated into several different contexts. And the key thing is they're going to learn both computing and the subject that they are working with. So I talk about statistics, but we also work with history teachers and civics teachers and general social studies teachers, as it's called in the US, social science, what you'd call it here. We work with teachers in the subject so that they actually learn something about their subject in addition to learning computing. So they're learning algebra, they're learning statistics, they're learning history, they're learning civics while also learning computing. And that's critical because if you don't do that, they are not going to adopt your materials, right? Physics teachers don't wake up in the morning saying, I really wish I could teach computer science today. If they wanted to, they would have taken computer science in college, right? They're not like fallen computer scientists. They're actually perfectly reasonable people in their own right. They are physicists. They are history teachers. They are perfectly reasonable human beings, and we are not the center of their universe, and that's perfectly fine. So what we do is we flip the script and say, we have to make sure our materials appeal to the people in those disciplines so that they can make sense out of it and use those materials in their subject. Okay? And we've got like very good diversity numbers, et cetera, et cetera. And our overarching goals are we care about three things. We care about three things because any one of these things is easy, two of these things is hard, and all three is extremely difficult. One is we want equity. Equity means we want to like maximize the participation of students. And in computer science, this is quite hard to achieve because there's all kinds of curricular things we can do that leave students out. And if you want to talk to me more about that, happy to talk more at length about it. Secondly, we want to do this at scale, like we operate all across the country, 49 different states, we have some international users. And finally, we want to do something rigorous. There has to be some depth to the content. If you throw this out, it's very easy to achieve scale in particular. Like Scratch is used all across the country. It teaches almost nothing, and everybody gets to check a box saying computer science done, prime minister is happy, chief minister is happy, your president is happy, whatever, to pick your political system, and they go home and students haven't learned anything. That's not what we are after, okay? So we want to achieve all three of these, right? And we even put it in our logo, because every day when we make a curricular decision, we look at all three things and decide whether to do something or not. So I want to tell you about the centerpiece, which is this Bootstrap algebra curriculum. Okay, and so I've told you about these very high level, this high level view. Our methods are to use, and this is why you're here in the room, is to talk about visual media and games, and just the amount of computing necessary to accomplish that. And our goals are, somebody talked about engagement earlier and retention, but we also have a very critical curricular goal, and the curricular goal is functions. Functions. Why functions? Why are functions critical? Okay, here's what we're going to do. I am going to say something and you are going to respond. Okay? Ready? 3 plus 2. 7 minus 3. X plus 2 equals 7. I can't hear you. Say it again. So here's the thing. I never asked any of you a question. I didn't ask you a question. I just said X plus 2 equals 7 or something like that. And what happened? You have all been trained to implement an algorithm. F of X equals X squared. Silence. Why? Because until you get to functions, mathematics is procedural. You're taught algorithms. You're taught addition tables, right? Tables are like a fixed algorithm. Then you're taught like how to add like big numbers. You're taught like carry things and stuff like that, right? Then you're taught multiplication. Then they teach you long multiplication, division, long division, right? And then they say, what if you have a variable? If you have a variable, you have to move things over to the left, move things over to the right, right? Divide on both sides. And if you divide on one side, not the other side, they'll yell at you, right? Everything is an algorithm. It's a procedure that is beaten into you till you can no longer help doing it. And now when I say f of x equals x squared, there is no algorithm. There's nothing to do, right? F just sits there as an inert object because it is abstract. There's no longer an algorithm you can apply. It is the first time in your mathematics education that you are introduced to abstraction. Now, technically, you've been introduced to abstraction all along. You just didn't realize it. Okay? So you're introduced to abstraction. What's even worse is now the math curriculum pulls this other trick on you. It starts to ask, like, I mean, is F into or onto, right? You're like, wait, now we are asking you abstract questions about abstract objects. Guess which point kids start dropping out of math education? Okay, so this is the critical part where math education suddenly takes a turn, a dramatic turn towards the abstract. And there's a lot of literature in math education about this material, about what happens to students' mindsets. For example, students start changing their verbalization of their struggle with math from saying math is hard to I can't do math. The first is a universal shared experience. The second is a personal feeling about their relationship to a subject. Okay? It also happens cleverly around the same time, various things are happening to, hormonal changes, etc. All this stuff happens at the same time. So there's a whole bunch of like social stuff going on as well that makes the math education problem even harder. Okay? So this is the pinch point. If you cannot do functions, you are not going to be able to do STEM. You're not going to be able to do physics. You're not going to be able to do chemistry, mathematics, engineering. You're also not going to be very good at like economics, business. A whole bunch of disciplines get closed out. Okay? So my goal is not to create more computer scientists. God knows we don't need any more, right? My goal is to make sure that this critical subject, people don't drop out of mathematics so that they have access to all these subjects down the road so they can make smart choices of their own. Okay? That is our fundamental goal here. Okay, so how do we teach functions? Well, what does it mean to teach functions? There are two things involved in functions. One is how do you compose functions? The other is how you define functions. Okay, now you've all had the misfortune of a school math education, right? So you all know how to teach function composition, right? You say something like, okay, so I'm going to give you a problem and you're going to tell me the answer. Okay, so f of x equals x plus 3. G of y is y squared plus 7. What is f of g of 14? The correct answer is who gives up? I mean, maybe it's 237. Is it? Could be. Do you care? Yeah. Okay. So let's try something a little different. Okay. And now the tricky part is going to be figuring out how to do this on Zoom. Okay, good. All right, so I'm going to do something different. We're going to write some code, okay? So I have here a little cricket bat icon, okay? Let's break it down. Let's do, yeah, I certainly can. How's that? Okay? Okay, so what have I just done? I have constructed a rectangle, right? Okay, so well, does that look like something? It looks like a cricket pitch. What if I were to call this the blade of a bat? Okay, so I'll call this the blade of the bat. Okay. Okay. So, okay. Actually, maybe we want to orient it vertically instead. So maybe we could do it this way instead. Let's do look a little more like a blade. Okay. I'm making mistakes on purpose, by the way, right? I want us to understand that we can explore these things. I'm using functions to draw pictures, right? I'm calling these functions. So how do I get a bat out of the handle and the blade? How do I get a bat out of the handle and the blade? Someone yell it out, yell it out. All the people who are reading Instagram or whatever you're reading back there. How do I get a bat out of a handle and a blade? Join them, how? Compose, how? How? What is the composition I'm looking for? Sorry? Juxtaposition, like I want them beside? Want them beside? Append? Or I don't know, we could try append. We could try above. Right? What if we tried above? Yeah. Okay. So notice what I did. I did two function calls, and now I have composed the results of two function calls. Okay. Now, what if what's the bat actually doing in the emoji? It's what? It's hitting the ball, but it's also doing it an angle, right? So okay, so we can call this the bat. Okay. Sorry. So 30. Like that? What's a ball? A circle? Yeah, go on, give me a radius. 10, solid, red, right? Like that? I've never programmed this language before. That's very impressive, right? Okay, you're starting to see the game here? Okay, how do I get the ball over the bat? What happened? Behind the bat. It's behind the bat? It's behind the bat. Are you telling me that you actually care about the result of a function composition? Oh-ho, okay. Okay, but then we didn't actually want that, right? We wanted getting there. Okay. So what is going on here? Okay, what we're doing is we start by teaching a notation for function composition. We call this circles of evaluation. We introduce students to this. One of the problems that students struggle with is understanding the structure of algebraic formulas. Okay, and the circle notation is designed to help students understand the structure. It's anyone do Indian schools still use the notion of like diagramming sentences? You learn like verb phrases, noun phrases, things like that. Draw a tree. I had a teacher who did this for a little while. I didn't understand what was going on either. Don't worry. Even if you saw it, you've probably forgotten it. But the point is, you parse a tree, you parse a sentence, right? You understand the parts of speech, right? The same way an algebraic formula also has parts of speech, and this shows you the parts of speech. But once you have done that, you go into the computer and you start writing code, right? And what you notice is that when you are doing the same kind of function composition on images, all of a sudden you start to rather care about the output, right? Because the output is not like 237 versus 219, it's the image that you were trying to create, okay? So the project is create your own logo, okay? And the important part is own logo. You may not care about cricket. Certainly in the US, unfortunately, they don't. But your logo is something you care about. And so you use function composition to build up your logo in exactly the same style as I showed you a moment ago, right? I want to show you one example from one of our students who's not exactly would never identify as a math person, right? But this is one of the starters, right? That's the logo they wanted, and they were willing to write function compositions, what, about like 7 levels deep, right? Because they have that as their output. So all of a sudden, the way you think about function composition changes, the way you care about function composition changes, and you start to see functions as productive things that do things that you care about, rather than a thing that your math teacher made you learn about, f of x equals x squared plus 3, right? So this is the way we get students over the hump of composing functions, all right? Any questions at this point? Good. Okay. So now let's get to the harder part, maybe, which is function definition, okay? So here's what we're going to do. We're going to do an exercise that's very common in math education. We talked about it a little bit just before this meeting with a few people, called what do you notice and what do you wonder? We'll just do a what do you notice part. So I'm going to give you this worksheet, okay? And let's just take 2 columns. What are the things in the game and how do they move? Okay? That's what you're going to do. I'm going to show you a game, okay, for a few moments, and you're going to tell me what are the things in the game and how do they move. Ready? Yes? Yes? Good to go? Okay. So here is the game. I'm going to play it for a moment. It's sad. Oh well. Okay. What are the things in the game? People, come on. What are the things in the game? Sorry? There's a, just name individual things. The ninja cat, exactly. There's a ninja cat. Name another thing. What's another thing in the game? The clouds, the diamondish thing, the background. What else?
Green dog.
Sorry?
Green dog.
The green dog. I think it's actually a cat. I think it's a cat. I know it's a little ambiguous looking cat, if you ask me. What else do you see?
Score.
Score. What else? There's a sun. What else?
Instructions.
There are instructions. Yeah. What else? The sun. Okay. You're missing. I think many of you are missing something important from the game. Game over and yeah, ninja. The ninja part of ninja cat. Okay. So there's a ninja and a cat. Okay. The cat, the green dog, is a cat. Okay. So there's a ninja and a cat, and then various other things. Okay. And how do they change? How does the ninja change? Ninja transposes up and then comes back down. Okay. How does the cat change? The green dog. How does the green dog cat change? Moves horizontally. What else changes? The clouds. How do the clouds move? Horizontally. What else? The score changes. How? Yeah, there's some rules to score changing. What else changes? Yeah, the ruby or diamond or something, whatever that is. Yeah, I think it's a ruby, right? It looks vaguely ruby-like. Yeah. How does that change? It seems to move this way, right? Okay. So there are all of these things that are changing. Some things change, some things don't change. Okay? All right. So this is the game we're showing you. All right? And now the key thing is to understand that movies are a lie. Right? In fact, you can guess from the fact that things are called movies that there must be some marketing going on, right? Because there is no such thing as a movie. Now, I understand that in the countries of Hollywood and Bollywood and Collywood and so on, you might be like, sure, there are such things as movies. But why do I say there's no such thing as a movie? Because there's nothing actually moving, right? All that happens, even in the fanciest of movies, is you have a bunch of still frames, and if you show those still frames fast enough, it turns out your brain will play this amazing prank on you and fool you into thinking there is motion. Okay? Even like the best dinosaur movie has this property, right? like, the Toy Story, right, was created, like there's actually a textbook from Brown University on the wall in Toy Story, right, as a tribute to Andy Van Damme. Even that book will tell you that movies and games are just a sequence of still images. Okay, so we're going to try to exploit this idea, right? So what we're going to do is, for a game, we're going to identify what is the core information in each scene, which is what is the information that changes. Now, have you already identified that for me? Yes, you have. You just told me, like, what changes. So in this case, for example, there's some X position for the player, a Y position for a player, there's a target, there's a danger, right? And we're going to perform updates to get from one frame to the next. Okay? And this is the key part. This is the place where the computer scientists will screw up, right? Because how do we perform the updates? So one thing you can do is you can undraw the previous scene, change all the values, and redraw the next scene. Okay? Or there's something else you can do. You can observe that getting from this information to this information, that's just a function. It's a function that consumes some data and produces some other data. And getting from this information to this information, drawing, is just a function. We just did this, right? We just took data and drew an image out of it. So the same way we can take data and draw an image out of it. These two things are just functions. And remember, our goal here is not to create a video game. Our goal is to teach students about functions. That's our goal pedagogically, right? So students are going to write these two functions. So for example, how does the danger update its position? It takes a current X position and generates a new position. Okay, how does the player change their position? They take the current Y position, and then they take a keystroke, and depending on the keystroke, they change their position. How do we draw something? Well, we take the current XY, and we use the same functions that I showed you earlier for drawing the scene. Okay, these are just clean, pure mathematical functions. Okay, so what happens is, in the course, every class, the students are confronted with a new source of frustration. Don't you wish that in your game the player could loop around, the player could respond to keystrokes, the player could detect collision with the danger, etc., etc. Okay, so there's a series of progressions of challenges in games. That's how you think about games, right? New challenges. For every one of those challenges, you have to learn some computer science content. I'm going to have to teach you how to write code that does X. I'm going to have to teach you code that does Y. The key thing is, this is all to teach you some math content. Every one of these things, and so in particular, we had a post-lunch conversation about transfer. We want students to transfer ideas from here to here. So we teach these things in such a way that there's a strong structural alignment. So when you learn one thing, you can learn the other thing as well. Okay, so to go from here to here is not left implicit, and we hope you figure it out for yourself, but we explicitly teach you this thing. So students are learning math all the way, and they are realizing that math is a solution to problems they have in the design of their game. That's the key thing. That's the motivation for the math. Okay, and they're learning all this important programming content at the same time. And of course, when you're done with the game, you got to have a launch party, so you have a launch party at the very end. Okay, now, for every single one of these things, the students go through this multi-step programming exercise where they learn how to write a contract or a type in programming terms. They learn how to write examples, also known as test cases, and then they take an abstraction over the test cases and define the body of the function. Okay, that's in math, that's in CS terms. But every one of these has a math counterpart. In math, right, those things are called the domain and range. Those things are called the input-output tables, and those things are called the symbolic form. And you know what one of the major open problems is in math education that math teachers struggle to explain to students? That all these different representations in math are actually interconnected. Students see a graph view, a formula view, a table view, a domain range view, and they don't understand that these are all talking about the same thing. Here, it becomes obvious they're talking about the same thing because it's the same executable piece of code. So that is another major math learning objective that is satisfied by doing things this way. Okay? Now, And so we can talk about transfer, but I also, this is like, good, nice, formal academic stuff. But I also have this great quote from this person who's the head of the STEM Education Outreach Center at UT Austin, which is, this is the most Texan quote you can possibly imagine. Okay, now, let me ask you a question. So you all saw the Ninja Cat game, right? Are you really excited to write Ninja Cat? Sort of, maybe. Okay. Let's talk about what it takes. I told you at the very beginning that students get to work on a game of their design. Ninja Cat was not your design, right? Ninja Cat was my design. In fact, it's not even my design, it's Emmanuel's design, right? So the question is, how do we get students to actually take ownership of the game? Okay, here's what we do. So when you go into class, this is what math teachers do. They go into class, they say, hey kids, we're going to take a break from math, okay? We are going to do some video game programming for a while, right? And many kids get pretty excited. They're like, oh, video games, no more math, awesome, okay? And of course, what's your favorite video game? Somebody here, what's your favorite video game? Name something, come on. It's okay, the professors don't know you play video games, it's okay. They actually do know, don't worry. Name a video game, someone. Sorry? Undertale? Okay. Another one? Yeah, okay. Oh, even professors play video games, see? Okay. Any others? Sorry? Oh, yeah, okay, good. Okay. How much does it cost to make GTA? How much does it cost to make Age of Empires? Do you know that video games cost more than movies? Yeah, minimum tens of millions of dollars. The games you folks are mentioning cost like well over $100 million. Okay, so kids are like, haha, we're making a video game, right? They're like, no. Okay, here's what we're going to do. We're going to go around the room and see how much cash everybody has in their pockets. All right. So in typical US math classroom, it's like, I don't know, like about $17 or something like that. Okay, so maybe we're not going to build one of those games, okay? And the level setting is important. We're going to lower our expectations a little bit to what we're going to be able to pull off in the classroom, okay? Instead, they get this worksheet. And on the worksheet, they basically get to select 4 things: the background, the player, the danger, and the target. That's it. Those are the 4 things they get to select, okay? So here's an example worksheet from a student. Our game takes place at the beach. Okay, the player is a mermaid dog, maybe a mer-dog. By the way, the mer-dog can fly. Okay, the target is a fish-shaped dog treat, and the danger is a great white shark, which turns out can also fly. So this is a bit of an oddball beach. Okay, all right, that's it. That's what you get to pick. Okay, so the question is, what can you do? Well, you can create a lot of different things, right? I mean, I showed you Ninja Cat. Right? There's another game. There's another game. Any of these, anyone recognize any of this? One of these, the bottom right's actually based on another game. It's kind of like a famous game of some sort. I don't know it myself, but when I put it up, people are usually like, oh, that's a such and such game. I'm like, yes, I'm sure it's true. Okay? And the top left, I'll tell you more about. Okay? So here's the thing. From a mathematical perspective, these games are all isomorphic. They are the same game. Okay? And the question is, do these degrees of freedom change the way students perceive the games? So we actually did a study of this, and here's what we found. We asked a whole bunch of questions, and here are the 3 critical questions. One is, do you feel like you made a real game? Okay, and green is strongly agree, blue is agree, yellow is disagree, and orange is strongly disagree. Okay, and what you can see is about 75% of them feel like they actually made a game. The 25%, by the way, are the gamers, right? They're like, it's not a real game. Like a real game is like the things that we mentioned, right? Okay, but do you feel like your game is different from the game that others made, right? And even more students, even the gamers, feel like they made something different from what the other students make, okay? The vast majority of students feel like their game is different, even though from a mathematical point of view, it's exactly the same. exactly the same. And why does it matter that they're the same? Because if you let a class of 30 different students to do 30 different things, as it is, a teacher cannot possibly help 30 different students doing 30 different things. What's worse is that a teacher is a math teacher and they have only minimal computing training, right? So pretty soon what will happen is the student will start doing things the teacher doesn't understand. Then the student will start doing things the student doesn't understand. Then the student will get stuck and they'll come to the teacher and say, I'm stuck. And the teacher will say, I have no idea what's going on, and nobody is going to learn anything. Our goal is to make sure they get better at doing math, not at ending up with a class full of hackers who are frustrated, right? That's why it's important. But it turns out that the small amount of differentiation is enough, okay? And to me, in some sense, this is the most important part, right? Are you proud of your creation? And pride in your creation is the thing that motivates you to keep learning and keep engaging and keep learning, and not just build a game, but also learn the math in the process, right? So it turns out you don't have to build, like, GTA or World of Warcraft or anything else to be able to actually get the pride you need and feel the sense of ownership to be able to learn from the math. Okay. Here are some of the quotes. These are kind of fun. So, there's like, slots are cute, zombie marshmallows necessity, you're funny, thought we like dogs. But then there's more serious themes like I care about animals, right? Or I'm passionate about the environment, or I'm passionate about getting people to pick up trash, right? Or it's a true story that we changed the story facts a little bit, or my sister loves Batman, I made this for my sister, right? So you're starting to see a whole bunch of themes here from, personal ones, serious ones, environmentalism. Students are telling stories through their games using just 4 parameters. That's all it takes for them to be able to tell a story through it. This one I really like. Anyone see what's going on in this? This is a student who read about people blowing up satellites in space and said, we're polluting space just like we're polluting Earth. And so the idea is there's all the space junk. There's this big butterfly net that's supposed to sweep up the space junk, but you got to make sure an asteroid doesn't smash into you along the way, right? So this is a student telling a very personal, profound story about space pollution through just these 4 parameters in their game, right? And I particularly, this is a topic I love to argue about with Scratch people and the constructionists in computer science, because we're taking a diametrically opposing point of view to somebody like Seymour Papert and saying it takes a small amount of personalization to tell very profound stories. Okay. This is an interesting thing. So we've got 4 parameters, right? So what if you had the 5th parameter? Wouldn't that make it better? So we actually had a 5th parameter, and a 5th parameter was like an object that moved across the screen. When we had the 5th parameter, every game looked like a shoot 'em up game. So we said, what if we take out that 5th parameter? And we had a long fight about this, right? It's like, look, we've only got 5 parameters. If you take it out, that's even less customization. So we were very, very, very nervous about doing this. And the funny thing is we took it out and all the games got much more creative, right? And people who study creative disciplines, this is not entirely shocking, right? Unfettered creativity is often a problem, and really creative work often happens in the context of constraint, right? Great writing, great art often takes constraints into account and thrives on it. And so, like, when you talk to computer scientists, again, we feel like we're the special discipline, right? We have to be given unfettered creativity because it's the only way we can create anything at all. And I think that's pretty overrated, right? And hopefully this is some evidence. Okay, the last part I want to talk about, I think I can skip this. I think this is more like a math physics education point. I'm not sure it's of general interest. I think I'll skip over this. I'll pass on this, okay? Okay, last thing I want to talk about is, at the very beginning, I brought up accessibility issues, right? And what if you have visually impaired students? And now I've spent like 45 minutes telling you about a curriculum that is all about visual media, okay? So briefly, I'm going to talk about accessibility for visually impaired. We've worked on how you can write code if you're visually impaired, like designing systems by which people can write code through voice dictation. We've also done a lot of work on the IDE navigation. As I showed you our programming environment. We have 3 different programming environments, and for each of those, we've worked on IDE navigation. But the other critical thing is how do you interact? Like you may have seen, like we had this interactive mode, and that's built on this idea of like a conversation. It's like a chat bot, right? But the visually impaired community has spent a lot of time thinking about how you navigate conversational IDEs, and so we adopt their ideas for that. How do you describe colors? You want to describe colors in a semantically meaningful way. This was a cool thing. So Vint Cerf, who's one of the creators of the internet, Vint Cerf found out about our work and got pretty excited. So he donated us a bunch of Google AI credits. So when you import an arbitrary image, if you're a visually impaired student, you can sort of send that over to Google AI on the cloud, and it will read the message out to you, turn it into text, and give you a verbal description of it, right? Images that we build by composition, we retain all of that information. So if you know what a scene graph is, we retain the scene graph. Scene graphs are really good for verbalization, so you can read it out. And there's even more subtlety. Like if you're trying to describe values, there's a concept that the visually impaired community use called semantic prioritization in how you read out values. All of these things are incorporated. So there's a whole paper that describes this. So all I want to say is we spent a lot of time thinking about this. If you want to talk more, I'm happy to talk more. There are papers you can read, but we haven't neglected this point. In fact, like our ultimate test was we actually got invited down to a school for blind children in Alabama, and they ran through the curriculum. Had some rough spots, but they got through the curriculum. And one of the really interesting bits of feedback we got from them was they said, it's really neat because usually we are given a different curriculum, the blind curriculum. It was super exciting for us to be able to do the same curriculum that students at non-blind schools use. And that's not something we'd often get. So that was kind of cool. Okay, so I want to end by saying, first of all, integrating computer science to other subjects is really promising. It comes with a lot of challenges, right? It sort of flips everything else around. When you have a CS class and a CS teacher in the room, you can do all kinds of things. But you may not have a CS class. You may not have access to CS teachers. You may not be able to afford them. There may not be enough trained teachers available. Integrating into other subjects is really promising as a way of dealing with all these issues, but it produces all the dual challenges. How do you get a math teacher or a physics teacher or a social science teacher up to speed to be able to teach enough computing? And how do you create a curriculum that they are going to care about? And that requires like real profound respect for their disciplines, okay? It's not just enough to have pretty materials, right? Like this is a problem that a lot of computer science people want to do outreach. They put up materials that are really cool, and then they're like, well, it's cool material. Of course people are going to want to use it. In fact, what teachers need is a giant support structure. They need teachers' guides. They need student guides. They need worksheets. All the stuff I showed you at the very beginning, those are the things you need to provide if teachers are going to be able to successfully use materials, okay? You got to understand all the constraints of the humans and of the systems that they operate in. Again, something computer scientists are really bad at doing. And finally, it's critical to let the host discipline drive, not computer science drive, right? They have a discipline. They've done, they spent hundreds of thousands of years figuring out how to do what they do. You got to leave them in the driver's seat. If you walk in sort of this sort of very serious CS imperialist way of saying like, we're going to tell you how to do things, they won't even show you the door. They'll say like, oh, thank you very much. And then the moment you walk out of the door, they'll take your stuff and put it in the recycling bin. Okay? So that's some of the lessons we've learned. This is a curriculum. It's been super successful in several places. It's got great learning outcomes, and it is exactly the opposite of traditional computer science education outreach. So that's the end of my talk, and I would be glad to take questions, criticisms, concerns, comments, anything that you want, and fire away. I should also say, I know we're starting to run out of time. We started a little late, but for anybody who needs to leave, it's not rude. Feel free to leave. If you have other classes to get to or other things to get to, it's totally cool to leave. I'm not going to be offended, so feel free to leave. Yes? So we're across a whole bunch of states in the US primarily. The thing that's been particularly interesting for us has been, so in the US, I'm sure that something like this would never happen in India. A whole bunch of state governors declared, we're going to do computer science for everyone, right? They had a big signing, they had a big bill, and a big fountain pen. They signed it in the State House. They got all the video cameras. They did this. They got all their PR. And then they went off to do the next thing and didn't allocate any money for it, right? Because it's very easy to sign things. It's harder to allocate money. So states are now scrambling to figure out, because now they have a mandate from the governor. It's the law that you have to teach computing to everyone, right? And how on earth do we do this, right? So what has started to happen in many states is they're starting to realize we can't afford to get computer science teachers for every school. We literally don't have the money. Also, there aren't that many computer science teachers. And you may have heard CS is a pretty decently paying discipline, so we can't pay them enough. And how do you get people to come to like rural areas, et cetera, et cetera, et cetera, right? So instead of trying to teach the one computer science class, what they now do is they take Bootstrap materials across all these disciplines and do it across basically do the one CS class across 2 years. So they find that across the Bootstrap curricula, they can attain the same learning objectives, but they do it across 2 years, which I think is actually better, because they're learning computing in context in other disciplines, and they're seeing the same ideas over and over again in slightly different guises, which means they're more likely to learn it better than if you see it one time for like 2 days and then move on. So that's been a very interesting deployment story for us. And so similarly, the data science curriculum started to get interested in data science. That we've got a data science curriculum. There's a huge controversy in the US right now about what's called algebra 2 versus data science. People want to throw out a whole bunch of like the upper math curriculum in schools in response for data science, without realizing that real data science needs that curriculum. So we're working on that integration. And of course, now everyone wants to teach AI, something we're starting to work on. The AI part I'm sort of least interested in because it doesn't apply to other disciplines quite the same way, but yeah. So this has been interesting. This is part of also what, when I say like successful deployment needs, you have to understand the system, right? If I just walk into the local school and say, here, I'm going to tell you what to do, they're not going to do it. But if you spend enough time integrated into the system, then you kind of learn like what the actual constraints are. It is pretty, so the thing we tell people is Bootstrap is an extremely iconoclastic curriculum in an extremely conservative garb, right? Everything here is very conservative. What we're trying to teach is very iconoclastic, right? My ultimate goal is to significantly teach the way we teach calculus. I think calculus is one of the most profound subjects ever, and I'm still angry at my high school and college education for like misteaching it to me. And I think we have better ways of teaching it. And like, that's my ultimate goal. Like, I want everyone to like really love calculus and really understand what it's about. So that's the project. But I can't tell anyone that because they're like, calculus, right? Everyone gets like scared hearing the word calculus. Yes.
Integrating CS into other subjects, is the motivation to get deeper into the subject, or is it that computing is a necessity?
Great. So the question is, what is the purpose of integrating computing into other subjects, right? Is it to get deeper into the subject? Is it because computing is really necessary for that subject? I would say sort of all of the above and more, right? So one answer is, look, if you want to get computing into schools and you can't afford to hire computer science teachers and make room for computer science classes, the only option available is to go through the integration approach. The second argument is, maybe we can enhance the way those subjects are taught. So in US, for example, all schools are created on the quality of their math and English education. Other subjects don't really matter, right? So if we can move the needle on math education, that itself is an accomplishment. And if in the process we can also teach computing, well, then everything is better, right? So the other thing is like, why does everyone need to learn computer science? I honestly do not think everybody needs to learn how to write a for loop, okay? I think it's a completely pointless activity, right? People need to learn computing in as much as computing affects other disciplines, right? We already screwed this up with math, right? Why do we make everyone learn math? Because math is like this universal language that affects every discipline. How do we teach it? By removing it from every other discipline, putting it in its own silo and not showing you the connection to any other discipline, and then saying, well, I mean, surely you can see math everywhere, right? And nobody sees math anywhere, right? So why not avoid that screw up this time? Why do CS as this new standalone silo? Why not teach CS in every discipline in a way that contributes, clearly works with that discipline, so you can understand that CS is connected to that discipline? And now if you see it across 5 different disciplines, you might start to say, huh, this may even have some universality properties. right? I think that's really the strong. I mean, the previous answer I gave you all the bullshit that I have to tell, like, school departments and stuff like that, so that they're like, oh yeah, so you can improve math scores, great, okay. But the real reason is, if we believe computing is universal, let's not make the mistake that mathematics made, or that we made with mathematics. Somebody, I don't know who the actor is that made the mistake. Let's not repeat that mistake, right? Let's put it in different subjects so people can see the connection. And that's why I say you have to like respect the host discipline, right? If you don't respect the host discipline, then you're just trying to teach computer science. If you respect the host discipline and integrate computing in a way that respects the host discipline, now you're actually speaking to that discipline. And if those ideas show up in 5 different places, students will be like, huh, I saw that once before. I saw that twice before. How about that? Like, it's all connected somehow. And that would be a huge accomplishment for us as a subject. Okay?
Just a move on.
Yeah.
Google search.
Yeah.
So easy and intuitive. I don't need to know anything much. It serves my purpose.
Yeah.
So somebody comes to me and says, it is a tool that's skilled, and I don't. So if it is done very nicely, so somebody can take that viewpoint also, right?
So let me make sure I understand your question. So you started by talking about Google search, and you said Google search was easy, and
Google search is the user of Google search.
The user of Google search, right. From a user's perspective,
without knowing,
they don't need to know how to computer science. They get to type something, they get their answer. Okay, yeah.
I use it for illustrations, things like that. If somebody is able to provide it,
Yeah.
which essentially makes it so easy to use.
Yeah.
And if you have the domain knowledge, that is enough, and you don't need to know many things.
Yeah.
In each case, the need for learning computing, right, is more in the background. You don't need to really invest any time.
Okay.
You may be able to still reach your goal. So would that be an alternative?
So the question is, if we can design interfaces that are so easy to use that we can achieve our goals without knowing much computing, is that good? I think anything we can do that we can achieve good goals with minimal effort is good, because people are inherently lazy. So that's totally fine, okay? But the problem is, do we know then how to be critical about the thing that supposedly achieved the goal, okay? So I think there's a very good question in this sort of era of like ChatGPT, right? So let me give you an example. This is something that happened at my house. So we were having a conversation with our kid over dinner, and kid said, why do people hate Harvard so much, right? They said, well, people hate Harvard because Harvard is really, really rich, okay? And it's very powerful, and people don't like the amount of power that it has. So I said, for example, Harvard is richer than many countries, right? So we're sitting at the dinner table. I didn't want to take out a laptop and start Google searching and stuff like that. I had my phone, and I have a paid ChatGPT account. So I was curious to see what happens. So I asked ChatGPT, how many countries have I said, how many countries have a GDP that is lower than and then of course, like, well, there's the Harvard endowment, and then how much it draws off the endowment. So I said, given the Harvard endowment, assuming a 5% draw on the endowment per year, how many countries have a GDP that is lower than that number and have a population that is higher than the number of students at Harvard? Okay. Now here's what's really interesting about this. I asked this as a question, and what it did was translate my question into a piece of code. And then it ran the code in Code Interpreter and gave me an answer. I looked at the answer and I said, yeah, that looks about right. I know enough about the world to say that looks about right. I said, let's try this again with 10% GDP, 10% draw, and it gave me about 12 countries and looked about right. Okay. After dinner, I went to look at the code. Okay. What I expected to see was a chunk of code. So this is as easy as it gets, right? And not only is it easy, I mean, it produced sort of real-time answers over dinner so we could continue our dinner conversation. Not only was it easy, it's even given me the code so I can look at it later on. So I go look at the code, right? What I'm expecting to see is a data set and a query on the data set, right? I read the code, and it is a query on the data set, and the code is exactly right? I mean, I can read the code, it's 5 lines of code, and it's exactly the query I would expect. I'm looking at the data set, and it's also very helpfully provided a comment on top, right? And the data set has about 20 rows or so. Well, that's a bit odd, right? How many countries are in the world? A little bit more than 20. I don't know exactly how many, but it's definitely more than 20 countries, right? Like most continents have more than 20 countries. So that's a bit suspicious. And then, but it's got a comment about the data set. So like, let's read the comment. And the comment is, countries that have a GDP below such and such and have a population above the population of Harvard. Wait, but that was the original query. So that data set should be the entire answer. So where's the 20 countries? In fact, where the heck did the 20 countries come from? I don't know. So I take, like, the first row was like Afghanistan, okay? So I take the population that's given for Afghanistan, I put it into Google. I can't find that number on Google. I don't know where it's getting this population for Afghanistan from. So now all of a sudden I have no idea the super easy answer that is even easier than Googling. I have no clue how it produced that answer. I still think the answer is pretty close to right. Okay, and the numbers are relatively plausible. Like, I mean, I know enough about the world to look at the. I mean, I was a quiz kid in high school, right? Like all good Indian high school students. So I know these kinds of numbers. They're all credible, but I have no idea what just happened. So that's the problem, right? Automation. This is the kind of stuff that people are doing on a daily basis. Automation without explainability is extremely dangerous. The easier the interface, the higher the level of reliability we need, right? It used to be, like when I was in high school growing up in Bangalore, I knew literally no other programmers, right? Every line of code that I had was a line of code that I had written, like handcrafted with my own hands. I didn't have a lot of code as a result, but I knew all of the code that I had, right? Then I had a friend, Balaji, and Balaji had more code than I did. So suddenly my code base grew, right? Then I went off to college, my code base grew more. Then I found Gopher and my code base grew even more. Then I found HTTP, right? And then GitHub came along. Then Stack Overflow came along. And now there's OpenAI. So all of a sudden, the means of production of code has become really, really, really easy. What that means is the means of validation has to go much, 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 much higher. The easier it is to produce, the harder it is to validate. So if we can find tools that make our lives really easy, that's great, as long as we can make the validation. So we've shifted the emphasis to validation, right? It's still teaching for loops isn't teaching that, right? We've got to teach people how to verify, how to test, how to check, how to validate. That becomes the new skill, right? Sorry, it's a long answer for that question, but I think it's a great and important question for us to wrestle with. Go. Green dog.
Sorry, you spoke about was the level of customization needed for a student to select code.
Yeah.
Can you talk a little bit more about how you push the tension between generalizing the curriculum versus specializing based on the student's interests?
Yeah, that's a great question, right? And so it all comes. So the question is about how do you deal with this tension between generalizing and specializing, right? At the end of the day, it depends on what your learning objectives are. Okay, so there's a lot of curricula where you teach Scratch to students, okay? And students are allowed to go off and create almost anything they want. But the end of the day, there's almost no learning objective for the course. The objective is the students must have done some programming, right? That is an extremely low bar, right? It's like tennis. You can keep lowering the bar, lowering the bar, lowering the bar till there's almost no net at all, right? That is basically what Scratch curricula, most of the Scratch curricula are. There's not even a curriculum, right? It's here, I'm going to teach you something, you're going to click around, the cat's going to move around the screen, and then you're done, right? Computational thinking has happened, right? So if you have no learning objectives, you can give arbitrary amounts of like customization, right? If you have extremely tight learning objectives, you can't give students any breathing room at all, and that's a really bad idea, right? Because students are just going to be like stifled, right? So the challenge is figuring out the trade-off, and it's very much like it's sort of a multiplicative thing, right? So you want to make sure that you give enough customization so that students feel some sense of investment. Similarly, in data science, we let students pick the data set they want to work with, right? Because if I give you a data set, right? Let's say I give you a data set of like, baseball, right? Which is like this inferior form of cricket that they play in the US, right? Be like, baseball, who the hell cares, right? But if I give you a data set about cricket, you might be like, oh, that's really cool, right? Or, maybe you want to study fashion, or maybe you want to study music, right? If I give you the data set that appeals to you, you will automatically start generating questions, right? I like to say like almost every kid is an inborn data scientist, in the sense that if you get into an argument with somebody else, at that point, you'll gladly hit them over the head with data, right? Who is the best cricket batter of all time? Who is the best quarterback of all time? You're like, let me show you a statistic, right? The same kid who hates math will gladly show you a statistic if they can prove their point, right? So when it becomes personal, we're glad to study math and statistics and all these other subjects, at least up to a point. So you need some customization for ownership, but too much means you lose control of what learning is happening, how to help students. Are they on a path? Can you redirect their path? Can you correct their path? And do they learn anything at all, right? And our point is, you don't need a lot. Small amounts go a long ways, and after that, you're just losing curricular gain in return for not much value. Does that make sense to answer your question? Cool. Other questions, comments?
Interaction, someone raised this issue of interest. You said you wanted to ask.
Yeah, there was the point about curricular selection. Yeah. Yes.
One question I had is, it comes to the question of transfer. That, I think so. Take on the compositions of the function that is in the design of art, the actual algebraic composition.
Yeah. Yeah, so the question is, how do they go from composition here to composition there? And that's part of the curricular progression, right? One of the boxes is about function transfer and learning about this form of transfer, and then they see transfer in more mathematical settings and realize it's the same idea again, right? And then they sort of get assessed on it later on, and then that's how you determine that they did actually transfer it. Right. Go ahead. Yeah, so the question is, can you do this in a literary setting? I think you could. The problem is the moment you get into like pure text, now you have to get into natural language parsing, and now you have to bring in this whole machinery of statistics, and now all of a sudden the prerequisites go way up. And that's why we haven't. Also, I think literature teachers already feel sufficiently disrespected that I don't think we need to disrespect them further by saying, oh, and you too shall teach some computer science now. So I actually kind of like literature myself, and I think I'm okay leaving them in peace. Yeah, they've got enough. They've got enough like politicians breathing down their necks, so they don't need me as well on top of that. Yeah.
In Bootstrap, is there you have mechanisms for you to receive indication on how well it's working?
Oh, there's a great question. How do we know how well it's working? So we work a lot with teachers. We get some feedback, and we can sort of see a little bit. One of the so there are two major issues. One is it's actually hard to get data out of schools because American schools have very stringent privacy requirements. Student privacy is taken super seriously. And so it's very difficult to get data out of most schools. But the other thing is, like, we are big believers in privacy too. So the three main people behind Bootstrap, Joe Politz, Ben Lerner, and Pirate, Joe Politz, Ben Lerner, and I, used to do web security research, right? And we did a whole bunch of research on web security and privacy, and we decided it would be super hypocritical of us to spend all of this time doing research on this, publishing papers, building systems, and then we turn around and build the pirate language. We're like, oh, but let's just stick in as much telemetry as we want in there, and then we can just hoover up all this data from students, and wouldn't it be great? And we decided that would be like extraordinarily hypocritical, and even we weren't that hypocritical, right? So we actually choose to be very privacy protecting, which makes it hard for us to get some of the data we'd like, but that's okay. I'm actually very comfortable with that. In fact, the latest piece of work we've done is we actually work with Roblox. Some of you may know it's like a game platform. We work with the Roblox company to figure out how to do privacy protecting telemetry. And so we have a lot more ideas about how to do privacy protecting telemetry now. And I think we might try to incorporate some of those ideas into Pirate eventually to be able to learn more, right? Because Roblox, what happens is, you have users everywhere from like ranked beginners to game studios develop on Roblox, right? And they've got like professional games on Roblox, right? Like real money changes hands. And you had to be like, we were trying to study like error messages and programming errors, and there, even an error message can leak the name of a function which could reveal a trade secret, right? So you have to be super careful with that data, and they would not be happy knowing that some random third party at Brown is looking at their data. Also, I didn't want that data, right? Because now suddenly if I get that data encrypted, whatever, it's like a huge risk for me to deal with that data. So that's why we worked on this privacy protecting data telemetry thing. And yeah, so I think I'd like to figure out ways of doing it, but we're very like careful about intruding. We also don't want students to feel like they're under surveillance because that's going to affect their learning. Right. Oh, plenty. Plus we have systematic. I mean, I showed you those papers, right? So we actually have controlled studies and things like that. Now we've got all of the research behind it. There's a whole web page full of research results. We do. We have anecdotes, everything. We have qualitative studies, all of that. We just don't do telemetry. That's the one thing I feel strongly about. Yeah. Yes, please. Yes.
And spoke a little bit about how to make the programming part of it. I was wondering if, if you could talk a little bit more about the outcome. Is that because it's a visual video game? How is that?
Yeah. So the question was, I talked about accessibility for visual learners, and I talked about how to make the programming accessible. And the question was about like the video game part, right? Yeah, the outcome. So we do a lot with that too. So for static images, so one of the things is we worked closely with a blind programmer for 2 years. So that was part of the process, right? It's like design-based research here, and we worked with a blind programmer. And so it turns out, visually impaired and especially blind people listen at a very, very high rate, right? Several hundred words a minute. That's their main input stimulus. And so what you have to do is you have to figure out how to turn everything that you see on screen into text. Once it's turned into text, then they're very good with it. They know how to work with it. So part of it is you have to work through the, what's called ARIA, which is a web standard. So the web standard for accessibility. You have to work with ARIA to make sure all the elements are properly annotated with ARIA tags for navigation and so on, because it's basically the tree-shaped view of the web page is something that they understand very well. But the other thing is, how do you make each component into text, right? So if it's a picture that is drawn by composition, we preserve the structure by which the picture was created and turn that into text that reads out what the picture looks like, right? So for example, this would turn into a black rectangle, the cricket bat, right? A black rectangle named handle over a larger, over a 20 by 10 black rectangle, over a 50 by 20 tan rectangle with a red circle overlaid and offset by a following amount, right? And so that's what you see, that's what you would hear, right? And for videos, we do it on a frame by frame basis, and they can sort of say next frame, next frame, next frame, and they can do it on frame by frame basis. So it's for a sighted person, you'd be like, well, that sounds a little not quite the same, but it's better than not being able to access anything at all. And I said, at least in small scale, the students really seem to enjoy it, but also for the function composition part, that part works really well. The video is a little messier, but the function composition part works really well, which is already an important math learning objective. Does that answer your question? Thanks. Hi.
So in the US, the students is more flexible, like you said, there are lectures and everything. But versus if I compare to India,
yeah,
education is very strict, very particular. We have 60 to 50 people in a class, and if we were to implement Bootstrap in India, there will be a lot of hurdles if I do the same.
So the question is, if you try to implement Bootstrap in India, because there'd be a lot more hurdles. Now keep in mind, I didn't say this, so you can't keep this in mind, but I'll tell you now. We really, really want Bootstrap to work for all students. So there are lots of electives there are some electives in the US system, sometimes less than they say. My kid has electives, and the school has told my kid which electives to take, so elective, yeah, okay. So like, it's like elections in some countries, I guess. So even though there are electives, we don't like working with elective classes because those tend to be very stereotypical in terms of like gender distribution and so on, right? We really want to go into the math class that everybody is already taking and be able to have an influence there, right? So in some sense, we don't want to work with these elective classes. So let's talk about the required math class, right? So you said there'll be hurdles to implementing Bootstrap in India. You tell me what you think those would be in a required math class.
Yeah, for example, CBSE is very strict. Like you have 12 questions, you have the exact answer to questions. Exactly. I don't know how the ecosystem works.
It's not that different, okay? So in fact, when we go to math teachers are maybe the most conservative teachers in the US. And it's because, as I said, math and English are the two subjects on which schools are graded, right? And there's like publicly rated, the amount of funding they get depends on. So you can go to a school that has like a 14% passing rate in math and say, how about we try this? And I'd be like, no, why not? Your pass rate is 14%. Yeah, but what if it becomes 13%? Like, you're 14%, how much worse can it get? They're like, no. I'm barely making it by 14%, don't do anything here, right? It's really weird. So there is that dynamic in the US as well. The key thing is the math teachers have a set of learning objectives they have to meet. If you can go in and say, you need 20 hours to do this, we're asking for 5 extra hours, but we are going to check off exactly the same learning objectives, then they're willing to talk to you. If you can't do that, they won't even give you the time of day, okay? Even then, it's hard to get them to experiment with things. You have to find ways to ease them into it. So here is an interesting thing that happens in the US system. In the US, exams happen before the end of the school year, right? So the school year ends like typically end of June, exams happen in like end of May, early June. So there's 1 or 2 weeks at the end of the school year, which is kind of like a dead time, and teachers are trying to find ways to fill it. Okay, so what we say is, well, you got that dead time at the end of the year, right? Always struggle to fill it? Yeah, why don't you try Bootstrap there? And anyway, students are kind of bored. They're like, oh, games, that would be kind of a fun way to do something. So they start off there, they gain confidence doing it 2 or 3 years, and then slowly they move it earlier and earlier into the school year, right? They start off with a week, then they do 2 weeks, then they do 3 weeks, then they start moving it earlier. So even in India, even in the US, it has to be done very conservatively rolling out. Again, if you walk in and say, do the following, they'll be like, thank you very much, and send you right back out. Right? So I think it's feasible. I mean, it does require teachers to be willing to try something a little bit new. I went to school in India. I know what an ask that is, but yeah. Hi. How would you assess creativity? I don't know. I don't even try, right? My goal at the end of the day is not to tell whether a student was creative. I want, in some sense, I showed you those graphs. That is the students telling me whether they thought they were being creative, okay? If they felt they were being creative, I feel no reason to second guess them. I don't want to be judgmental about them, right? What I care about is that they learn math at the end of the day. If I go into a math class, I care that they learn math, right? If they got enough creativity out of it to feel like they felt ownership of the material to learn math, that's a success for me, right? I'm not a creativity evaluator. Does that make sense as an answer? Yeah. Yeah, I think there are people who are much more qualified to answer that question. I'm not, right? I just want students to feel like, yeah, this made me feel like I'm in control of my curriculum. Because if you feel in control, you're much more likely to learn. Yeah. Okay. Yes, hi.
I was just curious, why is there a lambda?
Oh, why is there a lambda? Because we're like functional programmers. It's our secret symbol. It's our bat signal. A little call. Yeah, there's lambdas all over the place that you might not realize. Yeah, we're very lambda oriented. Ask this guy about lambdas. Hello.
So you talked about embedding CS learning in other domains.
Yeah.
Will that change learning in those domains?
Yes. Yes. The question is, yeah. Yeah. So the question is, we've talked about embedding CS in other domains. Will that change learning in those domains? I hope so, at least a little bit, right? And I do think that most subjects are being altered by CS. Okay, there's no question to my mind that they are being altered. Back in actually 2005, I created a course at Brown called Intro to Computing for Humanities and Social Science, right? And my particular focus was social science. And the reason I was focused on social science, I had this feeling that we were going to start getting these things by which, like, we were going to be able to study sociology in new ways, right? This was a year before Facebook, but MySpace was around. I had a feeling like MySpace had something to say about sociology. Right? And then, of course, we got Facebook, and then, we also got Cambridge Analytica. So it turns out it had way more to do with sociology than any of us would have liked it to. But the answer is very much yes, right? I think every subject, especially social sciences, have been profoundly impacted by computation. I actually started grad school as a computational biologist, right? And there's no question biology was revolutionized by computation as well. And physics even before that, right? I mean, like, in fact, if you go back to all the original uses of computers, right, ENIAC and stuff like that, what were they all used for? They were all used to project, find where's a bomb going to land, right? That's fun. There was all about solving differential equations for the military, US military, right? So physics was affected, chemistry was affected, computational chemistry is a big subject, biology is affected. That's all obvious because they're STEM disciplines. Math is now undergoing a revolution, right, with like proof assistance. But also the social studies. So yeah, I think every one of these subjects is profoundly affected, at least in a small way, at least in a corner, and then it starts spreading out in just the same way that math affected all these subjects. So yes, absolutely.
Modes of learning.
Yeah,
The subject is
that's correct. That's correct. What you work with, like data sets now, are pervasive, right? But the question we have to ask ourselves is, when we teach, say, a universal computer science class, are we actually teaching that? That's a questionable claim, right? Right. Yeah.
For instance, radical proof.
Yeah. 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 Like, you work with Lean, right? Yeah. Yeah. He's a good person to talk to. Yeah. Somebody had a hand up here? Yeah.
Are there any drawbacks you see to this curriculum?
Are there drawbacks to this curriculum? I mean, there's a drawback to, yes, for sure, right? You could have a class where the teacher doesn't really know what they're doing, and now they've just like squandered a whole bunch of time. You could also end up with a poorly taught version of this could end up turning students off from computing completely, right? So I think there's sort of like obvious perils over here. Our point, and so there's sort of a Hippocratic principle, right? Do no harm first. But then you also have to put that in the context of existing math curricula, and which is more harmful, trying this or not trying it. It's not completely clear to me. So yeah, no, I'm not blinkered enough to say there are no harms, for sure. I'm sure there's things that can go wrong. There's a hand up over here. There was yeah.
So when you talk about integrating time, when you mentioned not wanting to recreate mistakes in mathematics in terms of universal scope in other areas, but I was interested in the tendency to be from something called PCM. As in, and integrating computer science. What about computer science as this? It does some as you when it is being from
Right. So is it right? So there's an interesting question here, right? If CS is universal and we teach it inside all these other subjects piece by piecewise, this very piecewise way, what about CS itself, right? I think there is. Look. I mean, I'm a dyed-in-the-wool computer scientist, right? I'm a professor of computer science. I live, breathe, eat computer science. I love computer science as a subject. So it's a little difficult for me to stand up here and say like, CS, overrated. So I do think that a little bit, even though I love it. But I do think it would make sense to teach computer science as a subject after you've been exposed to it in these other disciplines, right? You see it. I mean, what the papers I talked about study this phenomenon called transfer that I talked to a few of you about earlier. Transfer is this question of if you learn something in context X, can you use it in context Y? Right? And everybody likes to think certain things are universal, and it turns out every time you actually evaluate it, they are not. Right? And the example I gave, the first famous papers on transfer were back in like 1906, where white males in America of certain economic status were expected to learn Latin. Why'd you learn Latin? Because Latin structure is so beautiful and logical. It will make you a smart, a better thinker and a smarter human and maybe a better dresser or something like that. And it turns out none of those things were true, right? Then people are like, oh, music is universal because it like shapes your brain and like helps you think logically and whatnot. And it's very mathematical. And it turns out, nah, not really. Nobody learns any math from music. Okay, sorry. Chess, right? Why should we teach everyone chess? Everyone should learn chess because like it makes you think more logically and clearly. And turns out chess makes you better at chess. That's it, right? Transfer doesn't occur, right? So there is so people are not very good at abstracting, right? What does transfer require? I learn it in this context. I have to then abstract out the features so that when I see it in another context, I can recognize the features, even though all the superficial details are different. The deep structure is the same, and I've understood the deep structure well enough to recognize it. When you put it that way, it's like unsurprising that it's really, really hard, right? How are you going to learn the deep structure from one example? You're not. That's one example, right? You need to see like at least 3 examples before you see that there even is a deep structure and know what the commonalities are and what are the superficial parts, right? So I feel like there's a lot of value to learning a little bit of computing through integration in several different subjects, right? Starting in about middle school. And first of all, learning those subjects differently, learning how to do things. And as you do this 3-4 times, you start to say like, I feel like I've seen this before. I feel like, and your brain starts to form the schemas. And then when you take a computer science class with like CS on the tin, now you're like, oh, yeah. I know how to do that. I know how to do that. And now I'm learning what the abstractions are. And then I learn these more universal principles, right? So I think it makes sense to do a CS class after you've seen a bunch of CS. And I think we could improve math education too if we did it this way. We don't have control over math ed, but we can control CS ed at least. You had a comment?
Yes.
That's okay. Go ahead. Think of that.
One question that what do you define any kind of interest that you actually use the language and find it? Using an unfamiliar language will often help people get the capture.
Yeah, I am, much as I would like to impute various magical powers to pirate, I'm not going to, because I haven't studied those questions and I don't want to make statements that I don't have data for. So I don't know, possibly. I certainly see some of those effects at the college level, but it's mostly like I would be giving you anecdotal data rather than something I can stand behind, right? I don't want to talk about programming languages. Like every computer science curriculum ends up talking about programming languages, and then like it's like Godwin's law basically, and then yeah, nothing good comes of that. So we can talk about that offline separately, but I don't have data to say that's true, right? I know we designed Pirate to be really good for curricula like this, and it seems to work well for curricula like this, right? And data-centric curriculum. The great thing about controlling your language, building your own language, is you can control every single thing that goes through it. So you can decide this is the curriculum I want a really good language for, and then you can build a language for that. Right? That much I can say it's really good for. Beyond that, I'm reluctant as a scientist to say more. Okay. All right. I think you've all been extremely patient, and you're all probably exhausted. So I'm going to let everybody leave and take a break. Thank you all for coming. Yeah, I think I am actually at some point this evening. I don't know when.
Wait, the lights go off.
What's going on with the lights? Power outage. Yeah. Even in Sri City, I thought like this is like the magical future, land of the future. No?
It's not the future we wanted.